All right, that brings me to the main topic of our class. We're continuing where we left off. We're a little bit behind schedule, quite honestly. Maybe I should do less ad blocks in between. But anyway, there's not going to be more, I don't think, in the lecture. So we talked about fitting functions to data. And in fact, a lot of machine learning is about fitting functions to observation data. You know, often people want to learn about learning. What is learning? Learning is a lot about function fitting. That you have measurement data, and yet you try to fit a function that allows you to generalize, to look beyond the observation data and make predictions. And this, you know, in the end, machine learning is a lot about making predictions from models that we learned from data. And here the data are the yi basically are the signal that we want to fit to, and then we have predictions yi hat. And what we discussed last times is this loss function that's called the least squares loss function, a quadratic loss function, where we say the prediction and the observation should be similar in terms of this least squares fit. And one can ask, is that a good loss function? Is that the best conceivable loss function? Is there a more principled way to come up with loss functions? And the answer is yes, there is. So this is in some way the simplest estimator because once we optimize it, we get a linear equation out for the unknowns. That's really nice. There's lots of different estimators, lots of different loss functions that you can consider. For example, here, if you fit a number to a set of numbers in the least square sense, then you get the average, the mean, as the optimum, right? And this is often very sensitive. We saw it to outliers, meaning if you have one outlier, it can significantly modify your prediction, your model, your inferred model. And this is something you often don't want. And then you would maybe go, rather than having a quadratic loss, you would just penalize the norm, for example. Then you're more robust to outliers. And there's lots of different losses, hinge losses or other, that you can try to use. And we'll talk about some other loss functions throughout class. What we'll talk about now is how to derive loss functions in a more systematic manner. And there is this idea of maximum likelihood estimation, something that you may have encountered before in other classes. The idea is fairly straightforward. We have a probability distribution that basically, P data of y given x, that is the true underlying distribution. What does that mean? Let's say x is an image and y is the label. Cat, dog, mouse, whatever, right? And you want to say what is the most likely label given the measurement, given the observation x. And what you do in machine learning typically is you consider a parametric family of conceivable distributions that are parameterized by some hyperparameter theta, and then you want to make sure that these parameters are determined in the learning process such that you best fit the probability, the true underlying distribution. The problem is you don't know the underlying distribution, but you have observations, you have training data, and these are sort of samples from that underlying distribution. And so the idea is that you have an underlying distribution, you get observation data from the true distribution, and that tells us something about what is the distribution and what it should be, and then you choose the parameters. For example, you can find the maximum likelihood estimate, what is the most likely set of parameters theta to fit the observation. And then you make IID assumption. This is a core term in this community. IID stands for independent and identically distributed. That means all your training data are independent. I take a lot of images from cats and dogs and whatever, but each image is not dependent on the previous one. This is an assumption that you make. Whether that assumption is valid is actually questionable. For example, if your input is video and you take consecutive images from a video, they're not independent. because you are recording with the same camera over time. So what you're going to see in image t is likely the same as what you saw in image t minus 1, right? So this is an example. If you just take video and take all the images of a video as input, they're not independent, right? So this assumption may not always be valid, but we'll make this assumption that the observation data is independent and identically distributed means it's all sampled from the same underlying distribution. And then, and then you try to maximize this probability. What is the most likely probability of y given x, and maximize this over theta. The problem with that is, and why can we do a product here? You know, we have lots of observations. The reason why we can factor this into a product is because of this IID assumption. This is something you might remember from, you know, basic probability theory. The probability for two events, A and B, is just the probability for A times the probability for B if they're independent. Right? For example, if you throw dice, right, the probability for throwing 6 is 1 over 6. The probability for throwing twice 6 is 1 over 6 times 1 over 6. Why? Because the two dice are independent. I throw them twice, and so I can just multiply the probability for the first dice to be 6 and then times the probability for the second one to be 6. So in the same vein, if we assume that the observations are independent, we can factor it into a product over all observations and the respective label. Now, products are not nice to deal with, and so what people do in the community is rather than maximizing this product of probabilities, they apply a logarithm to it. Why is that? Well, the logarithm is a monotonous function. If your function is maximal, then the logarithm of that function is also maximal. So you can either maximize a function, like the one above, or you can maximize its logarithm. It comes out to the same. Wherever this attains a maximum with respect to theta, this expression, which is the log of this product, also attains a maximum. And what we've used here is that the log of a product is the sum of logarithms of each term. So this is a typical property. Log of A times B is log of A plus log of B. Right? So we use that here. And so that means we can optimize not a product, but a sum of terms where each is the log of this probability. That's good. So we use this property of log AB is log A plus log B. Nothing very profound, really. But it means that the optimization problem of inferring the parameters is one of maximizing a sum of expressions. And here I should say, by convention, you can either maximize the sum or you can minimize the negative of this sum, right? Whether you maximize some expression or you minimize its negative is again equivalent. And depending on what you do, you would choose one or the other. And in fact, when you talk about loss functions, typically the loss function is the negative logarithm of the probability. Right? So if we apply a minus here, then we would look into minimizing this expression. But let's keep it with a plus. So there's this maximization. This is basically the question here is, what shape does our probability distribution have? You know, we have a model that makes a prediction. We have observations. They may not coincide with the prediction, but they should be close to what we predict. And then the question is, close in what sense? How are they distributed around? How are the observations probabilistically distributed around the model prediction? And there's many models that we can use for this conditional probability, but the most common model in probability theory that you would always use by default as the most simple one is a Gaussian distribution. You know, the classical Gaussian bell curve, right? So it would mean that, you know, this is a Gaussian distribution. We're working with these linear models, right? Xi times theta. Theta are the unknowns, xi is the input. So the prediction of our model is that yi should be xi times theta. But then what we allow here is that the true yi may be, or the observation yi may be distributed around the model prediction with a standard deviation sigma. So xi times theta plus a zero mean Gaussian distribution. It's called Gaussian distribution or normal distribution. Here's the formula. This is the usual, exponential, this bell-shaped curve. So far, so good. If we take this probability distribution and plug it in here, then basically we get this. We get, the prediction of the model, xi, y, and the observation, the label that we have in the training data is Gaussian distributed around our model prediction. See, so yi minus xi theta squared, and then exponentiate, and then this is a normalization factor. So this is one potential probability distribution. You can think of others, but let's start with this one and see where we get. So we take this distribution and we plug it into our optimization problem, finding the most likely model parameters given the training data. Xi, yi. Now I plug in this probability distribution. Once I apply the log to this whole probability distribution, I get a sum of two terms, right? Here it is. If I apply the log, here it is, to this expression, then I get this term, and then this term. Because again, log of a product of two terms is the logarithm of one term plus the logarithm of the other term, and then we have all these, and then we can pull the sum inside, so we have this term, and then we have a sum of this term. And that term, the first one, is the constant. It doesn't depend on the parameters theta that we have in here, right? It's constant. So once you maximize or minimize, it doesn't actually matter. It's just a constant, so you can just as well drop it. And so what we have to maximize is this expression, and that is the same as minimizing this quadratic discrepancy that we've talked about last time. So what you observe is that this least squares optimization that we introduced last time to fit our model to the data, this comes out from a probabilistic reasoning if you apply a Gaussian distribution and do maximum likelihood estimation. How do we determine the parameters? We want to maximize this with respect to theta, or we can put a plus here and then minimize this expression. We just set the derivative to 0 at the extremum. The derivative is 0. Remember from high school, if you have a function, you want to find a maximum or minimum, then its derivative with respect to the unknown must be 0. If you do that here, this is a quadratic cost. You'll see a little bit more in the exercises how this is done, but then you get this linear equation that can be solved in this fashion. So we're back to linear regression. And so what we found is that, again, the derivation details we'll study in the exercise session, but what we observe here is that maximum likelihood estimation, when I use a Gaussian assumption, it leads to a least squares estimation. That might sound surprising. Wow, we have a connection, right? It's not. If you know history, it's not. In fact, that was the whole point why the Gaussian distribution was invented. Gauss did not call it Gaussian distribution, by the way, right? That's the later world called it. And in fact, what Gauss did when deriving the Gaussian distribution, you think, well, how did he come up with this weird exponential thing, right? Well, he set out to solve the following challenge. He said, what is the probability distribution such that the maximum likelihood estimator is the least squares optimization, such that I get the average, the mean out as an optimum. And that's how he found the Gaussian distribution. So the connection that we just established between maximum likelihood with Gaussian distribution leading to a least squares estimator, that's what it was invented for. You know, that by design it has that property. But it's nice to see that connection. Often in literature they show you that, you know, surprisingly the least squares estimation pops out. No, it's not surprising. It was designed for that purpose. And what we also introduced here is this concept of loss functions and optimization to obtain the best model parameters to fit data, observation data, this problem of regression. But, you know, I set out, and a lot of the deep learning is about classification. Now we're talking about fitting functions to data. How about classification? This is a particular case where we have to fit functions to data, but these are not arbitrary functions. It's not like the temperature in the room that changes continuously. No, we want to assign a label to each image. How are these two problems connected? At first glance, they're not. But we'll see in a second that you can convert the linear regression to a problem of classification and to our first neural network. A single layer neural network, if you will. We'll come to that. So let's start with, let's look into how can we tackle this classification problem. Let's say we're given a set of images, and for simplicity, we assume, and this is always my recommendation, whenever you do research, start simple, right? You can always ramp up the complexity later. So classification, simple, 2 classes. So we assume every image is either a dog or a cat, nothing else, right? And that's already complicated enough, as you can see. The variety, the complexity is quite breathtaking. But still, let's tackle it. So we want to label each image 1, 0, if you will. 1 for cat, 0 for dog, or vice versa, doesn't matter, right? So this is a binary label, meaning we want to fit to this data. The y value is just 2 possible values. It's not a real valued expression, it's just 0 or 1. So this is the difference. In regression, I fit a continuous output value, like the temperature in a room. In classification, I have 0, 1. Unless you have multiple classes. That's then the next step. Then you have maybe one of n labels. 1, 2, 3, 4, 5, 6, up to n. And each image has to get one of these labels, right? But let's start with binary classification, the case of 2 classes. So we learned the linear regression. What we'll now learn is a generalization of linear regression that is called logistic regression. And that converts the linear regression we've learned about to a classification problem. And here's the idea. Again, I take my input signal, that is in our case the image, as a long vector of color values or brightness values, doesn't matter. You take that vector in, you do a linear combination with a lot of weights, you sum them up, and that gives you a value. But the problem is that in general these values can have arbitrary size. And what we'd like to do now is we want to squash this so that we can have values in the range 0 to 1. And there are many ways to do that, and one is to apply this so-called sigmoid function. It's a function that looks like 1 over 1 plus e to the minus x. And if you think about this function, here's the function, right? If x is minus infinity, then this is very large, and then that essentially the whole expression gets 0. And if it's plus infinity, then e to the minus infinity is 0, so you end up with 1. Then in between, it smoothly transitions from 0 to 1. That's this function. So it's like a smooth step function. And what we do now, and so once you apply this, you get a function with values in the interval 0 to 1, and you can start interpreting that as a probability. For example, a probability that the value is 0, cat, or the value is 1, dog. And so in practice, what we will do is we will take the linear combination of our input values, the weighted sum over theta I xi, and then we will pipe it through this sigmoid function. in order to clamp it to the interval 0, 1, or to basically squash it to this interval 0 to 1 and interpret it as a probability. And in fact, that can be seen as a one-layer neural network. So this is how you get from a linear regression to a binary classification. You just pipe it through a sigmoidal function. So now we can do the same probabilistic reasoning that we did on the previous slide and apply a maximum likelihood approach for classification. So now we have our input x, we have a set of parameters theta, and we have an output y. And now x is a whole set of images that we will call x1, x2 up to xn. And each is a vector of color values, and y is a set of labels, and these are ideally 0, 1, object, background, cat or dog. Right, so here's your set of images, let's say, and each image is a vector x that encodes the colors of that image, and then the label that is either orange for the cats or blue for the dogs, let's say 0 or 1, right? And then we get this probability. Why do we get this probability? First of all, again, we have the IID assumption. We assume that these images are sampled independently from the same distribution. So we have a product over all our conditional probabilities. And then why does it look this way? Yi hat is what we said on the previous slide, is the probability for observing, for having a cat given the image that we are looking at, right? Let's say 1 is cat and 0 is dog. Then yi is the probability for observing a cat, yi hat, and 1 minus yi hat is then evidently the probability for it being a dog. If it's not a cat, it must be a dog. And so it's much like if you throw dice. You may remember that. I was just saying, if the probability for throwing a 6 and a 5, for example, is 1 over 6. That's the probability for throwing 6. Times 1 over 5 is the probability, 1 over 6 is the probability for throwing a 5. And here in the same vein, I have the label, yi, that tells me cat or dog. If the label is 1, let's say cat, then the probability should be this one, namely the probability yi hat is what I want to be the probability for this being a cat given this image. And in turn, if the label yi is 0, meaning I'm looking at a dog image, say this one, then this exponent is 1, and then I get, as a term in this product, I get 1 minus yi hat. So, yes. Oh, sorry. Yeah, that's weird. That's a good point. Thank you for pointing that out. Yeah, I should have a laser pointer. I guess I'll try to bring one next time. So what you see is you have two terms in the product, and you have a product over your n input data. And each term is either the first one if yi is 1, or it's the second one if yi is 0, right? And each time it's either the probability for observing a cat, in the case of yi equals 1, then I get yi hat, the probability for it being a cat, or the probability for it being a dog, if yi is 0, then I get 1 minus yi hat as the term in this expression. And so the total probability for observing for these labels for dog and cat, given all these images, is this product here. So this yi hat is this probability for yi being 1 given xi and theta. And similarly, 1 minus yi hat is the probability for yi being 0. And so this way I have a probability model for the distribution of labels given these images. And now I can, in the same way as before, say now find a parameter value, theta, a set of weights for this linear combination that I'm doing, such that I maximize this probability or maximize the log of the probability. Again, we use the log. Why can we do it? Because log is a monotonous function. That's important. If you maximize an expression, you can equivalently maximize the logarithm of that expression. And we do that because then we can convert this product into a sum. So once we apply the logarithm to this product, here is the product again. Once we apply the logarithm, we get a sum of logarithms, and we get a sum of these logarithms of these two factors with exponents yi and 1 minus yi. In practice, again, it's yi is always 1 or minus 1 or 0, so it's always one of the terms will be 0 anyway. And once you apply this, so again, we converted the product into a sum by applying the logarithm here to the probability. And then once you do that, you can apply the log to this product, and we use again the same rule that log of AB is log of A plus log of B. And the exponents also come down. Log of A to the power of B is B times log A. And so this is the usual standard rules of calculation with logarithms. We apply them here, and you get yi times log yi hat plus 1 minus yi times log 1 minus yi hat. And keep in mind, these yi's are always 1 or 0. So in the whole sum, there's always one of the two terms that's not actually there. Because yi is either 0, then the first term disappears, or it's 1, then the second term disappears. And so for each training sample, we have a loss function of this form. Right? Y loss, here I maximize this expression. In practice, I would apply a minus and then talk about loss functions that I minimize. Why do I do that? It's a pure convention. We could just as well maximize expressions, but by convention, people like to minimize expressions. It's equivalent. It doesn't make a difference really, but you have to stick to some convention. And so typically, rather than maximizing, you would now apply a minus to the whole expression, and then each data sample contributes to the overall loss by this expression. And this is a very popular expression in classification. It's called the binary cross-entropy loss. So do remember that it's a very popular term. And the issue when you read a lot of machine learning papers is that the authors throw around with lots of different loss functions with different names, the Huber loss, the cross-entropy loss, and there's lots of different loss functions. So with time you will figure out what is what loss, but you can easily look it up if you want. But this is a popular loss function for classification because it emerges kind of naturally when you convert linear regression to classification and you apply the sigmoidal and then you do maximum likelihood, then you end up with this. And this is actually used for binary classification. Then it's called binary cross-entropy loss. But then there's also multi-class classification. We'll see that later. And then it's related to what's called the softmax loss, also very popular in machine learning and in deep learning. And in fact, with time, with the class, you'll get to see a variety of loss functions. We've seen the mean squared loss for fitting, linear regression with a Gaussian distribution. You get a mean squared loss. Here, for logistic regression, this classification challenge, you get the binary cross-entropy loss. And that is the loss for each training sample. And since I have n training samples, I would have a sum over these losses. You can normalize with 1 over n or not, doesn't really matter. These are constants. And that would be the overall loss that we now have to minimize. Why? Because we applied the minus sign. We started with a maximization challenge, making the probability as large as possible. Now we applied the logarithm to get a sum. Then we apply the minus sign, and we end up with a minimization problem. And again, this is a pure convention. You could drop the minus sign and say maximize, In the computer, it's the same thing. Once you implement it, it really doesn't matter. Yeah. And for this loss, so this is what it looks like. So for each data sample from I through n, we get this binary cross-entropy loss in our overall loss function. By the way, there is a little bit of disagreement in what is a loss function, what is a cost function. Some people distinguish and say once you sum up over all your training data, that's the cost, and before you call it the loss. I don't know. I mean, this is pure conventions, whatever you call loss and cost. And for me, cost and loss are equivalent, really, but I know there are others who prefer to distinguish. And so in practice, once we use this linear regression, then for our predicted probability, we would get xi times theta and then squashed to a 0-1 interval by this sigmoidal function sigma. And that's what we would plug in, and then we can minimize. And so it's almost like maximum likelihood estimation we saw before for the linear regression, with one gigantic difference. First of all, obviously, we're not doing fitting data with a function, with a linear function, but we're doing classification, binary classification. But in terms of application, the biggest difference is this problem in terms of the parameters, theta, that we have in there, it is no longer convex. And that's a big issue. If you know optimization, you know once you have a convex loss function, then you can find the optimum, you can find it efficiently, and it's the global minimum. For neural networks, this is not the case. You can train them, you can apply whatever powerful algorithms you have, whatever software libraries the world offers, you are never guaranteed optimal solutions, unfortunately. Why deep learning works nevertheless, what can I say? To a large extent, it is a mystery still. If you are theoretically inclined, this is worth investigating. And there are people working on it. One of the leading people in the field is a friend of mine, René Vidal, and he's actually on campus here these days, visiting us at TU Munich. And he's looked into, why do you get good solutions with deep learning, even though you're minimizing loss functions that are highly not convex. And why is it non-convex? Well, already the sigmoidal function is not linear, but then you apply the logarithm and all of that, so it's definitely not a convex problem anymore. So there is no closed form solution. We cannot just solve a linear equation system and invert a matrix and be done. Like in the linear regression case, no, we have to throw some iterative solvers on it. And there is a gazillion of iterative solvers. The most powerful, not the most powerful, but the most commonly used technique is a technique called gradient descent. You may have heard of that technique before. We're going to look more into detail in class, how it works. In some sense, the current deep learning solvers are all based on gradient descent. And again, it's not fully clear to me why that is the case. There is other algorithms out there, Newton methods, and different variants of them, and proximal methods, etc. But why gradient descent is the method of choice for something that is highly not convex? I think it's partially because we don't really understand the loss landscapes well enough. Usually, once you better understand your loss function, you can devise a more targeted solver that is faster. But I think part of why neural networks often take days and weeks to train is because ultimately the optimization machinery is gradient descent based. Gradient descent is kind of the plain vanilla solver for any iterative solving problem. It's plain vanilla. It can be applied to almost anything, provided that it's in some form differentiable. but it typically never gives you the fastest results. But we'll discuss how gradient descent works and what the different caveats are. We'll discuss that later in class. So what's the insight from this lecture? We can learn from experience. We can, have some ability to infer the future. For example, predict from observation data by extrapolating with the functions that we fit to the data. And the other thing we observe is that even linear models are often pretty good to capture complex phenomena. So, for example, for predicting the temperature in this room, given the outside temperature and the season and whatnot, and the humidity or whatever, and the number of people in the room, these linear models will usually do a fairly good job. But it depends on what phenomena you capture. And obviously, weather is maybe a perfect example. Weather is rather chaotic as a system, and chaotic systems are notoriously bad when it comes to predictions, which is partially why the weather forecast doesn't work super well. If you've been wondering why the weather forecast often doesn't apply, it's because it's a chaotic system and prediction is maybe not easy. But next exercise session is a math recap, and then the next lecture that we're going to move to right now is going deeper into neural networks, literally speaking. Because in some sense, this binary classification can be seen as a one-layer neural network, and we'll look into how to make them deeper and why one would want to make them deeper. And we'll talk about computational graphs. A bit more of reference for further reading. This is on the slides. There is some literature that on the internet on cross-validation that is illuminating a little bit how do you do training, labeling, and test training and testing and validation. This kind of split that we talked about might come in handy when you develop your own neural networks to have a bit of background there. Also, as a general machine learning book, there's always the book by Chris Bishop, Pattern Recognition and Machine Learning. Chris has quite a talent in grasping recent developments and converting them into textbooks for students, and they're usually fairly popular. All right, that's all about the second part. I would then move on to the third part, and that is now Introduction to Neural Networks. I guess you've been waiting for that from the start of the class. Now here they come, the neural networks. But, they don't fall from the sky, and that's the whole point of this lecture, is to gradually move you to the neural networks that you see how they emerge. And the story is how we can get from linear regression, fitting a line through data points, and logistic regression, having a linear model but then doing a sigmoid to get a binary classification out, so converting the regression to a classification, and how that leads to the general neural networks. So here again, linear regression, we fit a linear model with parameters. There is the bias theta 0, and then these parameters xij, the parameters theta j for each dimension of your problem. So in practice, I often draw these pictures where x is 1D. In practice, x will be higher dimensional, right? And this is one of the big issues, that certain things, both input, but sometimes also the output, can be very high dimensional. And the goal is to find parameters theta such that the line that you're drawing approximates the data points. And we saw that if you do least squares estimation, it's like maximum likelihood with a Gaussian probability distribution. Then we talked about logistic regression, where we applied this sigmoidal function and converted this regression problem into a classification problem. The idea being that now I have a lot of data points, some represent cats and dogs, and then I have a distribution that is essentially binary, 0 or 1. So the y values are not distributed around a line, but they are distributed, they're binary. And so what I want to do is I want to basically binarize it essentially, and that's what we do softly with this sigmoidal function. to create then a probability for the label being 0 or the label being 1, whatever. And then we saw y hat can be the probability for y being 1, and 1 minus y hat is then the opposite, the probability for y being 0. Say dog or cat, if you will. And that way we can convert the linear regression into a logistic regression, into a classification problem. How do we obtain the model? We talked about it. You have data points, ground truth label data with cats and dogs, or, if you do linear regression, x and y, pairs of x and y value, you fit model parameters that gives you an estimation, and then you'd make sure that the estimation matches the ground truth labels. So y is always the ground truth, y I hat is the prediction by our model. And that can be a linear prediction if it's linear regression, or it can be for classification. We pipe this linear function through a sigmoidal to get a probability for some binary label. The challenge is then to find suitable loss functions, and that is often problem dependent, what loss functions make sense for your kind of problem. And then the idea of learning is that you optimize the loss function with respect to your parameters theta, to find the best parameters such that the predicted value y hat is as close as possible in terms of the loss function to the ground truth. And we talked about linear score functions, where the score is basically a linear sum of the weighted sum of the input values. In matrix form, you have a vector of scores f, and that is w times x, where w is some matrix and x is the input vector. So to give you examples how that works, you can fit a classification network to data, to images. And there are lots of data sets out there nowadays that you can use. This is one called CIFAR-10. This is a data set that contains 60,000 images, 32 by 32, so very small images, because compute is costly, so they started with small imagery, of 10 different types of objects, cats, dogs, whatever, right? Here you find them, birds, cats, deer, dog, frog, you name it, lots of different objects. And what you can do is you can actually train a neural network, and then you can visualize the W's. So these W's, if f is a vector of score functions, and for each class you have one score function, one matrix W, and then you can visualize that W. And this is what you see here. After training, we visualize the W, and what you see here is this actually looks like a horse a little bit, right? So it's kind of a blurred version of a horse. The reason why this works on CIFAR-10 is multiple reasons. First of all, there are only 10 objects in the data set. And secondly, these objects are almost always in the same position in the image, like the horse is typically in that area. If it was always perfectly the same horse in the same area, then we would see a very sharp horse image here. But since it's always slightly in a different area and slightly different colored horses, that creates a blurring, right? Especially the legs can be, in different positions. And then, so what we see here, roughly speaking, is actually the average of all the horses. That's what comes out as the feature vector. Why? Because in the training, we want to find a weight matrix such that if I multiply it with my input, the score is maximized if it's a horse. And the best way to maximize is if you take a horse image and multiply it with another horse, then you get a maximum signal. It's like, if you want to have a vector x that is maximized when doing the dot product with my vector, with my input, then you would take x itself that maximizes this dot product. So the way you can see this matrix W, every row of this matrix W corresponds to one class in these 10 classes, and there are 10 rows here for this data set. And if you multiply x with that row, you want to maximize it for the score function of the horse once it is a horse image. And that leads to this looking like a horse image. So this is a row of these are rows of the matrix W that are plotted here after training. And this looks like a horse. What's interesting here is you see a horse, and similarly you see something that is vaguely looking like a truck here. And so this network, even in the first layer, it basically computes, it correlates this input image with this weight vector. And once this is maximized, once the dot product is maximized, then it takes the score, and then it basically takes the score for the largest of these, where the score is largest, and then that would be the label that is assigned to this image. And what you observe is you get these blurred versions. What's interesting is here you see the head of the horse is sometimes to the left and sometimes to the right, right? So this is a horse with two heads, sort of, right? And that's because in the training data, 60,000 images, there's 6,000 horses in there. Some of them have the head to the left and some of them had the head to the right. And once you compute this, it creates an average horse, if you will. And that also explains a bit the blurring. The other thing you see is in terms of colors, it's the typical horse colors, right? This is this brownish color. Apparently most of the horses in the training set were brownish in color, right? And they were mostly standing in green background. That's why the background is green here, right? And you can see that is less clear for other objects where the colors, the deer is also brown on green, right? But for cars, it looks like most of the cars were somewhat reddish apparently in the data set. So you can infer that by looking at the rows of this weight matrix. And during training, this is the W rows after training. During training, these rows converge to the average image of a car, a horse, etc. This is all nice, and it shows you there is something we can get out of training, even a linear regression, a linear model on classification, this what we show here. But this starts to break down once you take bigger data sets and more complex data sets. So this is a bigger one. It's called ImageNet, one of the most well-known data sets in computer vision. This is a data set by a friend of mine, Fei Li, together with her students, Andrei Karpati and Johnson. They put out this data set. I think there were several authors on it. In fact, Fei made quite a career out of data sets. When I got to know her, she was a PhD student at Caltech, and one of her first papers was a data set called Caltech 101. It was a data set containing 101 images or classes, I don't know, of different objects in the real world with her PhD advisor, Pietro Perona, and we overlapped in Los Angeles. I was a postdoc at the time. And then she went on and she did more bigger data sets until eventually ImageNet. ImageNet is much bigger than Cypher10. Cypher10 is 60,000 images, 10 classes. ImageNet is bigger. ImageNet has 14 million images and tons of classes of objects. And there's more variety, right? So it's not only the brown horses in the same spot in the image, but they may be in different locations with different colors, etc. And as a result, for the various classes that you see here, you know, it looks much more complicated. Right? So you can, you can still infer certain colors from some of these classes. For example, certain things are clearly predominantly green or brownish or something, but it's much less easy to actually discern any specific object in these weight matrices. So again, these are rows of the weight matrix W after training on this huge data set, ImageNet. different locations, different size, different orientation, also different lighting, different, so it's just a much more real world data set. And you see that this is important, you want computer vision techniques to not work on kind of artificial data sets where the horse is always in the same place, and in the same color, but you want it to work on any horse in any color in any environment, right? And that requires you to generate the bigger data sets and then develop methods. And in fact, it was the ImageNet data set that sparked the whole deep learning revolution. Because this was the challenge. They said, well, these linear classifiers, they don't work on this real world data, or not very well, right? You can always get some classification rate, but it's just not very good. And then the deep networks came about. And what is the key difference? The key difference is if your training data is distributed like on the left, the cats and the dogs in the case of binary classification, or the circles and the triangles here. And you have a clear linear separation that separates one class from the other, then it's easy. Then you can fit, a linear classifier to it and you're done, using this logistic regression, for example, right? But what if the distribution gets more complicated? What if the horses are more similar to the dogs and the cats and whatever, and it's not possible to find a linear separating hyperplane that separates one class from the other? Then you have to move to nonlinear separating hyperplanes. And then a key question is, how do you represent nonlinear classifiers? And there's lots of different ways to do it. So, the question being, how can we make linear regression better, right? And you might think, well, if multiplying with one matrix works, why don't we multiply with another matrix, W2? So we have one matrix, W1, with lots of weights. We take a second matrix and we define a feature vector that is W2 times W1 times the input. At a first glance, that looks reasonable, right? You'd say, okay, twice as many parameters that I can fit. Good, I have a chance. Unfortunately, this is not the case. And that is because if you multiply two matrices, W1 and W2, it's equivalent to multiplying the input with just one matrix, and that is W1 times W2. Meaning, yeah, on paper you have twice as many parameters, but once you multiply them together, it's equivalent to taking a single matrix. So you haven't gained anything, right? So you have over-parameterized your problem, but in practice, you still have the same number of freely choosable parameters. Because there is infinitely many combinations of W1 and W2 that lead to the same product, W1 times W2, W2 times W1. And so the operator remains linear and there is no nonlinearity. It's still a linear classifier no matter how many matrices you multiply. It's like multiplying with a single matrix. You don't gain any expressive power. And this is something that's studied a lot. How can you increase the expressivity of models? And here's an elegant way to do it, and that is you introduce a nonlinearity to make it nonlinear. And so in principle, the idea is the same. Here's my matrix W1. I multiply with a matrix W2. But before doing so, I add a nonlinearity, like the sigmoidal that we talked about. And there's many, here's the sigmoidal sigma, right? You can use that one, but you can also use a truncation, where this is a maximum of 0 W1x, which means this is a function that is linear for W1x being positive, and once Wx1 is negative, it's just 0, it truncates. This is called a rectified linear unit. We'll talk about it later, ReLU. Very simple function, but extremely powerful, and it also boosted the success of deep neural networks, this introduction of that particular nonlinearity. You can use different ones though. You can also use a tangent hyperbolic here. Then you see I can make it more and more deep. by just adding sequentially a nonlinearity and then multiplying with another weight matrix. And I can do a 3-layer neural network by linear combination with W1, then nonlinearity, ReLU, then multiply with W2, again a ReLU, and then multiply with W3. And these are engineering strategies I can crank up, and I can do this, and it's been done up to easily hundreds of layers. And there are two aspects that have been studied. One is the expressive power. What functions can you represent? What decision boundaries can you encode with different amounts of layers of a neural network? And in fact, there was a big a big issue that led to the AI winter. People in the 90s did not believe that creating more than 3 layers was meaningful, because you can actually show that with one hidden layer you can represent any decision boundary. And so I have a colleague here in the building, Burkhard Rost. He worked on neural networks in the 90s, and he told me, he said, Daniel, this was our biggest mistake in the 90s. We thought that making more than one hidden layer has no value, because it's not more expressive, because you can represent any decision boundary with a single hidden layer neural network. But the issue is, in practice, it's not only how expressive is your neural network in terms of what decision boundaries can I represent, but the second question that was very much overlooked in the 90s is, can I actually find the right parameterization of that decision boundary for my training problem? So does this gradient descent on the non-convex loss function lead to a good minimum? A minimum that is as close as possible to the right decision boundary that I'm looking for. And this was the issue, that did not work in the 90s. With a hidden layer you could fit, you would find a solution, but that would be arbitrarily bad sometimes. And so neural networks in the 90s were considered not working. In the 90s, people decided they don't work. And I remember in 97, I sending an email to Geoff Hinton and many saying, I want to do a PhD in neural networks. They didn't even respond, most of them, right? And some did and said, this is a completely dead area. Why do you want to venture into this area? This was the belief in the late 90s, right? And what people overlooked is that there is an added value in going deeper. And the added value comes from not the expressivity getting larger, but the capacity to actually find the desired solution gets somehow magically better with more layers. My intuition is, once you have more layers, you can represent also any decision boundary, but there are more equivalent representations of the same decision boundary. Weight matrices W1 through Wn that essentially encode the same decision boundary. And if you randomly initialize your weights, the chance that you will find one of these is higher somehow, intuitively speaking, right? That's my intuition. I cannot prove that, and I don't think anyone has proven this. But that's roughly the idea why deep networks actually work, and why there is a value in going deeper to sometimes hundreds of layers. Now you see already here, I deliberately put different nonlinearities, the ReLU with this max 0 W1x, or the tangent hyperbolic, or the sigmoidal with this exponential function that we saw on the previous slide. Why did I do that? Because there is no consensus in the community which nonlinearity is the best. The sigmoidal, I believe, may have been one of the oldest. I remember studying that one in the 90s in textbooks. But the rectified linear came a little bit later, and it made some things more efficient. For example, the compute, and it seemed to work better in some cases. But to date, there's, as we speak, people develop new, different nonlinearities. We'll see some in a second. So this brings the single classification, the binary classification with the linear logistic regression, to neural networks, right? Just concatenating it with nonlinearities, matrix multiplication, nonlinearity, etc. And so that's a little bit the history that you can see that reflected in the history of neural networks. I showed this slide before. You see in the 1940s, Pitts-McCulloch, very famous, kind of the first neural network. It had adjustable weights, but they were not learnable. And then came the perceptron, where the weights were learnable, but it was a single layer neural network, if you will. So like, like what we've seen, the logistic regression, if you will. And then, people like Minsky, Papert, and others, threw attention on this XOR problem, which cannot be separated with a linear classifier. And so there was need for nonlinear classifiers. And that brought about in the 80s and 90s this multi-layer perceptron, the first nonlinear approaches for learning. And this whole algorithm of backpropagation learning that we'll learn about in this class. And then the deep neural networks came in the, in the 2000, 2010, something like that. And the great breakthrough then in computer vision and the rest of the world came around 2012 by applying these deep networks to the ImageNet dataset and to language modeling, etc. So the difference again is in logistic regression, you try to find a linear hyperplane that separates the two classes. In neural networks, for binary classification, you may have more complex images, like here, these two characters of the Game of Thrones video, and then you want to find a classifier that separates them. And so you do that by concatenating weighted sum of the signals and then some nonlinearity, let's say a rectified linear unit here. And you can do the same then as we did for the logistic regression. You can look on Cypher10 on other data sets. You can look at these weights of the first layer. For example, W1 is the first layer, and you can study the neural network at different levels of your network. You can, after training, look at each weight matrix and the rows of these weight matrix. Here they show you these images, right? In the first layer, the weights will have the rows of the weight matrix will by definition have the same resolution, the same dimension of your input signal. This may be different in later layers, right? But you see here for Cypher10 there are different cats here, activations of the first layer. So this is the one-layer network. On the left, a weight matrix, right? And then the output feature vector that you can then pipe through a sigmoid to get a labeling or a probability for a certain class. And then the two-layer network here, it looks like that. So we have a weight matrix that we multiply the input with, and you see these visualizations that are becoming very popular nowadays to encode this. Why do we do this? Because the equations get more and more lengthy, right? You can, in principle, write everything down like we do here on the lowest line, right? But at some point you don't see anything anymore with all these brackets and functions being applied to functions in a nested fashion. If you do that for hundreds of layers, you're good luck with reading the paper, right? It doesn't work. And so people start with graphic visualizations of this, and this is one way of doing it. You have your input X, you have a weight, and this could be 100 by 28 by 128, let's say. So the input is actually a vector of 16,384. And in fact, if it's color images, it's actually 3 times that, right? Because I have red, green, and blue for each of these pixels, right? And then I'd have a vector that is 3 times this length. And then I have a weight matrix W, that boils it to a set of feature vectors. And here, for example, the dimension could be 1000. Why 1000? This is your choice in modeling how many features you want to extract. And this is a design choice that you can either choose heuristically or you can think about it very carefully. Like when we first introduced deep networks, graph networks for protein prediction, we thought very careful about how many features do we want to extract in the first layer, for example, in this precursor of AlphaFold. So these are things where you know, if you tackle it for the first time, you have to think about how many features make sense to extract. And that's very problem dependent. And then you have a next matrix, let's say W2, and then in a 2-layer network, you would get again an output. If your problem has 10 classes, you would have a feature vector that has 10 rows. So the matrix W has 10 rows, and the output is a 10-dimensional feature vector for each input X. And then ideally, the feature value would be high if the object is of the respective class. So you have 10 values in your feature vector, and each entry corresponds to the probability for this being a cat, a dog, a horse, or whatever, right? So that's how you have to interpret this. In practice, you would often, in these deep learning approaches, you would often compress the input image to a lower dimensional representation, this H. This is often called a latent representation, so that you've heard this term before. It's a popular expression. And the idea of this hidden layer here that has a lower dimension, instead of 16,000, it only has 1,000 dimensions. It allows to compress the input information. And the key aim of all learning is to basically compress in a way that you get invariance. In other words, this vector should ideally look the same even if you have different cats in there, right? Or if you have the same cat but in different backgrounds. So it should, this latent representation should ideally abstract and from the things that you would call nuisances, the background that you don't care about, right? Such that the subsequent transformations lead to a classification where all cat images, independent of their background, will be labeled as cat. That's the aim. You can ask, why is that structure useful? There are many reasons for that. But one is that this layer-wise processing can be done super efficiently nowadays on graphics hardware, GPUs. But another thing is that this layer-wise processing is very similar to what happens in the human brain. As I mentioned before, there is an inspiration that comes from studying human cognition and human brain, and there we have a processing in layers. For example, visual input is processed in many, many layers of the so-called visual pathway. And this is 2 layers, but you can have more layers. And then you have these representations like you have them on the left, where you have an input layer, a hidden layer, or multiple hidden layers, and an output layer. And then you have these little arrows that tell you how, if you will, information flows, right? And so the feature here in the first entry of the hidden layer is a linear combination of the outputs of these neurons, right? Summed up and then piped through a nonlinearity, and that is then the input to the next layer, right? And whenever you have an arrow, so you typically get these graph-like structures, and every arrow corresponds to weights with which the input is then summed up in the next layer. And so these arrows, as many arrows as you have, this is essentially the weights of your weight matrix, but encoded here in this graphical visualization. So the weight matrix W1 that takes the input to the hidden layer, this is basically the weights on these arrows. They represent the entries of your matrix W1. And And so if you have a hidden layer, in this case of 4, so you don't have to take a compression, you can also expand like you see here if you want. So you have 3 input neurons and 4 in the hidden, then your weight matrix is a 4 by 3 matrix that converts a 3D input to a 4D output. And then you always have in each layer a weighted sum of the inputs piped through the sigmoidal or whatever nonlinearity. And this is often how we visualize these things. So what you have here as the first neuron in the first hidden layer is the nonlinearity f applied to the linear combination of the input vector x times this offset or bias b. And so that's how it is, and in each layer you have that. The function f here is the same nonlinearity, but you can choose different nonlinearities for different layers if you want, right? And typically these are fully connected in the sense that for each neuron here, all the input neurons contribute in that linear sum. Now in practice, once you train, the sum of these weights may go to 0. In which case it means that neuron does not depend on the respective input, right? Because it's weighted by 0, right? And sometimes this is something that you want. For example, if you want to compress neural networks, you want a lot of these weights to be 0 because then you have faster compute. Multiplying things with 0, you can just skip that as well, and then you have less compute effort. And so this is a big effort in compressing neural networks. Very often we don't write it out in this fashion, this whole mathematical expression, so we just, a lot of the neural networks look like that, and I bet you have seen gazillions of these images in the press, in the media. They always show this, the neural network, here's the picture. The laymen don't really know what this picture means, but now I hope you all understand what it means. That you have input signals, and that all of these edges here are the weights in your linear combination that define the output in the next layer as the linear combination of that input vector with the weights on these edges, and then the sigmoidal nonlinearity on top, and then that is piped through to the next layer, etc. Talking about activation functions or nonlinearities here, these activation functions, there are many. The sigmoidal one that we talked about, this is probably the oldest one, at least I've seen it in papers going way, way back. Also tangent hyperbolicus is an old one, and qualitatively they're the same. In practice though, people find one may work better than the other. Which one works better is really a lot of trial and error, and it depends on the problem that you're solving. The ReLU became really popular with the advent of deep networks. So this is this truncation. Here it is. If the input is positive, it's just x, and if the basically linear, and if the input is negative, you clamp it to 0. You can also do a leaky ReLU, and guess what? That came out after the ReLU. Someone found actually if you have a bit of leakage, meaning for the negative values of x it's not exactly 0, but it's 0.1 times x, so it's like also linear but with a 10 times smaller slope, or whatever slope you want. You can also learn the slope. This is then called the parametric ReLU, where you have a parameter alpha that defines the slope of in the negative regime, and then you can train that with the rest of the weights, right? Then you have a learnable activation function. And in fact, you could, in principle, learn the whole activation function, and people have looked into that, have tried that. You would not believe how many things people tried. Why? Because it's a hot topic. And any advance you make that improves classification rate or learning speed or whatever will have a massive impact in the world. And so all of these papers that introduced all sorts of epsilon variations, literally epsilon variations on activation functions, they had massive impact in the community. The max out is a more sophisticated one where you have basically what you see here with weights W1, W2, and B1 plus B2. So you can have fairly sophisticated, learnable configurations. Or the ELU is a little bit some hybrid between the rectified linear unit and these exponentially decaying things that we used to have, right? So when it's positive x, then it's just linear, and in the negative regime, it is a little bit like these exponentially decaying functions that we used to have. And it's such that at zero, it coincides. So you see there's gazillions of possibilities, and this is not all of them. There's obviously more, but this is just examples of activation functions that people proposed. Again, why do we need activation functions? Why don't we just multiply the matrices together? This is a really important message, and I hope you understood that. If you concatenate linear transformations, you are still in the world of linear transformations. The product of two matrices is nothing but a matrix as well. So you don't gain if you just multiply matrices itself. There's no value. There's no increased representation power. That's why you have to introduce some nonlinearities, and this is what they do here. Again, why, organizing neural networks in these layer-wise fashion? Well, first of all, it's very efficient on the GPUs. It says, so if you have software libraries like TensorFlow or PyTorch or whatever, they run very efficiently on these layer-wise processing for forward pass, but also for back propagation learning, right? Because they can process layer by layer, and then depending on how big each layer is, you need GPUs with sufficient memory so that they can process the layers simultaneously, etc. But there is also the biological inspiration that processing in the brain happens through neurons. Here is a visualization of a biological neuron. There is this relation. So in a biological neuron, much like in the artificial neural networks, you have neurons and they get input from the previous layer neurons, and that is maybe summed up in the nucleus of that neuron, and the input propagates into the neuron through what's called dendrites, and there are maybe many dendrites from which it aggregates information from other neurons. Then this is aggregated in the nucleus, for example, with a linear weighted combination or something more sophisticated, and then there is an output signal propagated along what's called an axon. So that is the output signal that is then carried to the dendrites of the next neuron. So far, so good. So there is this analogy, right? So here we have the biological neuron. Here we have our artificial neuron, where in what you could call the cell body, we aggregate in the sense of summing up in a weighted form the input coming through dendrites, if you will. And then there is an output, and that is the nonlinearity applied to this linear combination. So with this activation function f. So it looks at that glance very similar, right? But you have to be careful. It's about as similar as airplanes and birds, right? The airplanes are inspired from birds, but whereas birds flap their wings, last I checked, airplanes do not flap their wings, right? And so the analogy is very coarse. Here, the same thing. For example, biological neurons are very complex. You have lots of different kinds of neurons in the brain, and they behave very differently. And biologists, I've worked in this field myself for a year, and I've talked to many biologists. They love the complexity of nature. As a computer scientist, you'd want every neuron to be identical. Not so the biologists. They say, oh, there's the ganglion neurons, there's these neurons, that neurons, and they're all different. I said, that's not good. And biologists, they like diversity, and they like that aspect. That's one thing. And then the next thing is that the actual mechanisms inside a neuron are much more complicated than what we do in computer science. You have partial differential equations called the Hodgkin-Huxley equations. They govern the behavior of every neuron. And they tell you how the neurons communicate, and the neurons typically have a spiking behavior, so they send out spikes. So a lot of this is different. Now, there are lots of efforts to try to reproduce spiking neurons on a more biologically realistic level in computer science for image analysis. You can do that. I think there is potentially a value in it, but the question is always how much biological analogy do you really need to move forward? Because in the end, computers don't have the same hardware as humans, and there are many differences. One big difference, by the way, in biology that is really worth exploring is biological neural networks are extremely power efficient. The artificial neural networks that we use, I can guarantee you they're not, right? You train a neural network with tons of GPU, you don't want to see the power bills that we pay every month for the Munich Center for Machine Learning, for example. Just the energy cost is crazy, right? And this is a big issue. This is a huge issue. People don't realize that sometimes, that training something like ChatGPT will sooner or later surpass the energy need of an entire country, right? That's where we stand today, right? So this is quite frightening, and so there is need to look into energy efficiency. And biological neural networks have gazillions of neurons, yet you know how much energy you consume. It's much less than the GPUs that we have in the computers. So that is something that is explored in the neurosciences. I know, for example, a friend of mine in Cambridge, he published papers many years back on he called it the metabolic cost of signaling, where he studied fly brains and looked into how much energy consumption do they need. And he showed that some of what the brain does in the fly can be explained by energy minimization. How can I get the results I want in the most energy efficient way? And so there we still have a significant backlog over brains, real brains. But otherwise, obviously, this analogy to, our artificial neural networks are like the brain. The press, the media, they love it, right? In truth, yeah, there is some analogy, but you shouldn't overrate it. It's there are massive differences, and there may be value in looking deeper into how the human brain or how biological brains work and how we can reproduce some of these aspects. Power, efficiency, things like that. So back to, this is class not on biological neural networks, but on artificial neural networks. So let's go back to that. To summarize, given a data set with ground truth training pairs, we can find functions, we can fit data, we can find optimal weights and biases using gradient descent, stochastic gradient descent. We'll see that in a bit in this class, how that works, such that the loss functions are minimized, such that we can reproduce the training data as best as possible. By the way, one comment here, the notation in this class varies a little bit. I have this, W that encodes the weights. Sometimes I separate it from the biases, this B term that we have the constant offset, then the weights times the X, but sometimes it's all in one, right? So I apologize sometimes W represents both. So it's just the unknowns of your model. And that can include the bias sometimes. And we'll learn about stochastic gradient descent later. So the idea is that you compute gradients with what's called backpropagation and what's called the batch mode. We'll see more of that later. And then you basically iterate over your training set, typically multiple times. And the stochastic aspect, to say that up front, the stochastic aspect is that in every training epoch, you don't take all the training data in your loss function because it's way too big. if you have 14 million images in your training set, let's say, or 10 million, whatever, you don't want to evaluate a sum over 10 million terms at every time you evaluate the loss function. So you would stochastically randomly sample subsets of your training data in each training epoch and then fit to those and then resample and do that iteratively. And this is what's called stochastic gradient descent. The stochastic, we'll talk about it later, it has actually two benefits. One is it makes it more applicable. I don't have to sum over millions of training samples, so I can actually do things more efficiently. But also, by doing it stochastically, you get a robust approximation of the real gradient descent, and that tends to, let's say, stabilize the learning process a bit. There's less of an overfitting if you just at every iteration take a subsample of your training data. And so that's been shown to actually improve learning. One thing I wanted to introduce briefly is this notion of computational graph, because they play a role, because essentially a neural network can be interpreted as a computational graph. Computational graphs are directional graphs, and they're used quite frequently. So, they're used for auto-differentiation or symbolic differentiation methods. You may have encountered them in other areas of computer science. But one of the ways they help us is they allow us to compute derivatives. Because when we do learning and backpropagation, we want to propagate the discrepancy in the loss function to an improvement in my weights, right? How do I change the weights to get the loss to be smaller? And this information needs to propagate through the neural network backwards, right? So you have the forward pass that goes from the input to the output, and then you have the backward pass that propagates the discrepancies in the loss to changes in your parameters in each layer. And this is called backpropagation learning, and for that we can use computational graphs. Directed graphs where matrix operations are represented as compute nodes, and then all sorts of operators like plus, minus, divide, log, exponential can be represented as vertex nodes. They can be variables or operators. And the directional edges show the flow of input to the vertices, and they allow us to do forward passes and backward passes. So here, for simplicity, some examples. If you have this expression x plus y times z, you can write it as a computational graph in this fashion. As you see, it's not very profound, right? We have x and y, we do a sum, and then we do a product with another node z, right? And that gives us the output, right? And so, for example, if you want to then compute with this, you have initialization, 3 values for x, y, and z, and then you put them in here, and you can then, layer by layer, if you will, through this computational graph, evaluate that overall expression by going through this graph. And what we typically observe is, why do we discuss these compute graphs? Neural networks have complicated architectures. We've seen one of these, layered sums of weighted sums, nonlinearities, tons of matrix operations. I want to implement them efficiently, and for that I can use this representation of a computational graph. And I can represent the neural network as a computational graph and then do the computations based on that. So I can represent them as computational graphs. I have compute nodes, I have edges that connect the nodes, so there is a data flow. It's a directional graph, and then it can be organized into layers here, for example, for this more complex expression where I have Z2 being a sum of the inputs X with weights W and biases B, and then I can have an output layer Z3. So Z2 is the hidden layer and Z3 is the output layer, and this would be the computational graph to represent this expression. Which doesn't make it simpler, but it makes it more usable for computers. And so this way you can encode very big network architectures like this one. It's a paper called Going Deeper with Convolutions. And there you see that you have this abstraction, and the different colors encode different things, either convolutions or pooling or max pooling, a lot of functions that we'll learn about more. Dropout, etc. And this way you can easily visualize even very big graph and network architectures. And this is the compute pipeline. Yeah, so here's more examples. Activation functions. There's convolutional neural networks where you have a convolutional filter, basically a weighted sum of the neighboring pixels that gives rise to the value in the next layer. These convolutions are very popular in neural networks, and for example, convolutional networks are used extensively to extract feature information in images for classification. For example, with convolutions, you can detect edges in images and determine whether the shape of the object looks like a car or like a bicycle or whatever. And so these convolutional filters are used a lot there. That's all about computational graphs. I'll now come to loss functions again, and I think I'll stop here and we'll reconvene next week. Thank you.